Hi everyone, in this video we are going to discuss about pedal triangle. We will derive the length of each side of the pedal triangle and also will derive the size of each of the three angles of the pedal triangle, and we will derive the circumradius of the pedal triangle. So let's get started. Let's suppose we have a triangle ABC, that's our original triangle, where the side length AB is denoted by lowercase c units, side length BC is denoted by lowercase a units, and side length AC is denoted by lowercase b units. And the circumradius of the original triangle ABC, it is denoted by uppercase R. And also the angle BAC, which is near the vertex A, it is denoted by uppercase A radian. Angle ABC, which is near the vertex B, it is denoted by uppercase B radian. And angle ACB, which is near the vertex C, it is denoted by uppercase C radian. Now to draw the pedal triangle, the first thing we have to do is we have to draw the altitudes from each of the vertices onto the opposite side. If we join the feet of the altitudes, then that will form the pedal triangle. So let's see how pedal triangle is actually formed. So first what I am going to do, I am going to draw the first altitude from vertex A onto the opposite side BC. And let's suppose that the altitude is actually AD, which is perpendicular on BC. And because AD is perpendicular to BC, it actually divides the original triangle into two right triangles. One right triangle would be on the left hand side, which is the triangle ABD, and the other one will be triangle ADC. Each of them will be right triangles since AD is perpendicular on BC. Now if you look at the right triangle ABD, the angle BAD will be 90 degree minus B, because angle ABD itself is B, uppercase B. So then the other angle of this right triangle will be 90 degree minus B, or pi over 2 minus B. And similarly, if you look at the angle DAC, that will be 90 degree minus C, because angle ACD is already uppercase C, and then angle DAC will be 90 degree minus C. And also now let's talk about the length of the line segment BD. So BD is actually the projection of AB onto BC, and that will be lowercase c times cosine of B, because the side length AB is denoted by lowercase c. So then BD will be equal to the projection of AB, and that will be lowercase c times cosine of B. And similarly, if we look at the line segment DC, its length would be the projection of AC onto BC, and that will be lowercase b times cosine of C, because the side length AC is denoted by lowercase b, so its projection on BC would be lowercase b times cosine of C. Next I am going to draw the second altitude, which will be from the vertex B, and let's assume that that altitude is actually BE, that's the line segment BE, which is perpendicular to AC. Now here again BE divides the original triangle into two right triangles. One of them would be BCE and the other one would be BEA. And so if we look at the angles CBE and the angle EBA, you will see that angle CBE will be equal to 90 degree minus C, because if you think about the right triangle BCE, we have one angle which is 90 degree, the other angle is the C angle, and then obviously angle CBE will be equal to 90 degree minus C. And similarly, if you look at the right triangle EBA or ABE, in that right triangle we already have an angle A. So the angle ABE will be 90 degree minus A. Now if we look at the line segments which are CE and EA, now what would be the length of CE? Well, that will be the projection of BC onto AC, and projection of BC would be BC times cosine of C, that will be lowercase a times cosine of C, because BC side length is denoted by lowercase a. So CE will be equal to lowercase a times cosine of C, that's the projection of BC onto AC. And similarly, if we look at the line segment AE, that will be the projection of AB onto AC. Now AB is denoted by lowercase c units, so then AE will be equal to lowercase c times cosine of A. That will be the projection of AB onto AC. Now let's draw the third altitude. Here I have the third altitude, which is CF, and it is perpendicular to AB. And again, this altitude also divides the original triangle into two right triangles. One of them would be triangle AFC and the other one would be triangle BFC. In the right triangle AFC, if you think about it, we already have a 90 degree angle, and also we already have the A angle, uppercase A angle, which is near the vertex A. So the angle FCA or the angle ACF, that angle will be equal to 90 degree minus A. And similarly, if you look at the right triangle CFB, there again we already have a 90 degree angle which is near F, and we already have angle B, uppercase B, which is near the vertex B. So the angle BCF will be equal to 90 degree minus B. And here again, let's look at the line segments BF and AF. Well, BF will be the projection of BC onto AB. Now BC length is denoted by lowercase a, so it will be a times cosine of B. That's the projection of BC onto AB. And similarly, the line segment AF, that will be equal to the projection of AC onto AB. Now AC is denoted by lowercase b, so it will be lowercase b times cosine of A, that will be the length of AF. That's actually the projection of AC onto AB. So we have drawn all three perpendiculars here, meaning all three altitudes. Now what is the foot of the perpendicular? Well, if you look at the point D, E and F, they are actually the feet of the perpendiculars that we have drawn so far from the vertices, right? So D is the foot of the perpendicular AD, E is the foot of the perpendicular BE, and F is the foot of the perpendicular CF. Now if we join these 3 feet of the perpendiculars, that is going to form the pedal triangle. Now you see, we call it foot of the perpendicular and the name of the triangle is pedal triangle. You know, there is a relationship between foot and pedal, right? We usually push a pedal by our foot. So because the triangle is formed by joining the feet of the perpendiculars, that triangle is called the pedal triangle. So let's draw the pedal triangle here. I am now going to join the points D, E and F to form the pedal triangle. So here the yellow triangle that you see, that is the pedal triangle of the original triangle ABC. So triangle DEF is actually the pedal triangle because this triangle is formed by joining the feet of the perpendiculars drawn from the vertices of the original triangle. Next, we are going to look at some interesting geometry about the angles. Before we move on, let's also denote the intersection point of the 3 altitudes. It is actually the orthocenter of the original triangle, and the orthocenter is usually denoted by uppercase H. So I have denoted here that the orthocenter there, which is the point of intersection of the 3 perpendiculars, that's the orthocenter of the original triangle ABC. Now if you look at the quadrilateral BDHF, that's a quadrilateral BDHF. Now in that quadrilateral, you see there are 2 right angles which are kind of the opposite angles there, angle BFH and angle BDH. Those 2 angles will be right angles. So we have a quadrilateral where the sum of one pair of opposite angles is equal to 180 degree. That means this quadrilateral is actually a cyclic quadrilateral, and I'm going to draw a circle here to show you how that quadrilateral is a cyclic quadrilateral. As you can see that quadrilateral, the quadrilateral BDHF, it is actually a cyclic quadrilateral because there is one pair of opposite angles whose sum is equal to 180 degree. So angle BFH and angle BDH, each of them being 90 degree, their sum would be 180 degree. That means it is a cyclic quadrilateral. Now because it is a cyclic quadrilateral, now we are going to look at the chord DH and see what are the angles it is subtending. Well, if you look at the chord DH, it is subtending the angle DBH and also it is subtending the angle DFH. So those 2 angles will be equal because the same chord subtends equal angle on the circumference of the circle. So here I am going to denote that with a pink arc here. So we have angle DBH, which is pi over 2 minus c, and it will be same as the angle DFH. So I am going to denote that with a pink arc right here, the angle DFH, I am denoting that with a pink arc. So angle DFH and angle DBH, they are actually equal, and we have already proved that angle DBH is equal to 90 degree minus c. So angle DFH will also be 90 degree minus c. I am just denoting that with a pink arc there. Because of lack of space, I am not writing pi over 2 minus c there, but it is actually pi over 2 minus c. Similarly, if we look at the FH chord, the FH chord will also subtend equal angles on the circumference of this circle. Now one of the angles would be FBH, which is 90 degree minus a, and the other angle is FDH. So FDH will also be equal to the angle FBH, and I am going to denote that with a light green arc right here. So the angle FDH is also equal to the angle FBH, which is actually 90 degree minus a. Now I am going to remove this circle and we are going to look at another quadrilateral. let's take a look at the quadrilateral CDHE. And if you look at that quadrilateral CDHE, there again we have two angles which are 90 degree each. CDH, that angle, and the angle CEH. Each of them would be 90 degree angle, so their sum would be 180 degree. So the sum of the two opposite angles in this quadrilateral, this pair of opposite angles giving a sum of 180 degree. So then this quadrilateral is also a cyclic quadrilateral, and I'm going to draw a circle here to show you how the quadrilateral CDHE is actually a cyclic quadrilateral. As you can see here, the quadrilateral CDHE, that is actually a cyclic quadrilateral. Now let's look at the chord DH. So the DH chord subtends two angles here, right? One angle would be the angle DCH and the other angle would be angle DEH. Now both of those angles will be equal in size because the same chord subtends equal angle on the circumference of the circle. So then angle DCH, which is 90 degree minus B, will also be equal to the angle DEH. That means angle DEH will be equal to 90 degree minus B, and I'm going to highlight that with a yellow arc here. So wherever I just did the yellow arc for the angle DEH, please assume that that is also equal to 90 degree minus B. And also let's look at the chord EH. Now if you look at the chord EH, it is also subtending two angles there. One of them is ECH, angle ECH, which is 90 degree minus A, and the other angle is actually EDH. And if you think about it, the same chord which is EH, that chord is subtending these two angles, so these two angles better be equal. That means angle EDH will be equal to angle ECH, which is actually 90 degree minus A. So I'm going to denote that with a light green arc over here to denote that the angle EDH is actually equal to the angle ECH. I hope things are clear up to this point. Next, we are going to look at another quadrilateral which is towards the top of the original triangle. So now let's look at the quadrilateral AFHE. If you think about that quadrilateral, there again we have a pair of opposite angles which are 90 degree each. That means their sum would be 180 degree. That means the quadrilateral AFHE is also a cyclic quadrilateral. And let me draw a circle there that will clearly show you that that quadrilateral is also a cyclic quadrilateral. And as you can see here that the quadrilateral AFHE, that is also a cyclic quadrilateral, and the angle AFH and the angle AEH, each of them is equal to 90 degrees, so their sum would be 180 degree, which is again a pair of opposite angles in this quadrilateral. So this quadrilateral is a cyclic quadrilateral. That means if we look at the chord FH, the FH chord is subtending two angles there. One of the angles would be FAH, angle FAH, which is 90 degree minus B, and the other angle that the FH chord is subtending, that is actually the angle FEH. So FEH angle would be equal to the angle FAH, which is 90 degree minus B, and I'm going to denote that with a yellow arc. And now let's look at the chord EH. The EH chord is also subtending two angles there. One of them is the angle EAH, which is 90 degree minus C, and also it is subtending the angle EFH. So angle EFH will be equal to the angle EAH, which is 90 degree minus C, and let me denote that with a pink arc here. So I have denoted the angle EFH with a pink arc to indicate that it is also equal to 90 degree minus C, which is equal to the angle EAH. So our construction is complete now. Now we are going to calculate the size of each of the angles of the pedal triangle. Let's look at the first angle, which is, let's say, EFD. So what would be the size of EFD? Angle EFD is actually sum of the two pink angles that I have denoted there. That will be 2 times 90 degree minus C, because each of the pink angles is actually equal to 90 degree minus C, and we have two of them there. Those two angles actually form the angle EFD, so that will be equal to 90 degree minus C plus 90 degree minus C. So that would be like this. That is one of them, and the other one is also pi over 2 minus C. And if you simplify it, this is actually pi minus 2 times C. And what is the uppercase C here? Well, that is the interior angle near the vertex C of the original triangle. So angle EFD is looking like pi minus 2 times C. And similarly, let's look at the angle FED. Now angle FED is looking like sum of two yellow angles, and each of the yellow angles would be 90 degree minus B. So we can write it as pi over 2 minus B plus another pi over 2 minus B. And if you simplify it, this is going to become pi minus 2 times B. And let's look at the third interior angle of the pedal triangle. That is the angle FDE, and that is looking like the sum of the two light green angles, and each of them would be 90 degree minus A. So then this angle of the pedal triangle will be equal to sum of the two angles, each of which is equal to 90 degree minus A. So we can write it as pi over 2 minus A plus another pi over 2 minus A, and that is going to give us pi minus 2 times A. So if you look at the pedal triangle, each of their interior angle is actually pi minus 2 times the opposite angle of the original triangle. That's an interesting observation here. Now let me highlight this. So we have been able to find the size of each of the interior angles of this pedal triangle. Now we are going to see how to find the length of each of the sides of this pedal triangle. Now in order to do that, we have to understand one more piece of geometry here. Now if we think about the angle BDF, for example, let's look at the angle BDF can be written as angle BDH minus the angle FDH. Now what is the angle BDH? Well, BDH is actually 90 degree, so I am going to denote that as pi over 2, and minus what is FDH? Well, FDH is actually 90 degree minus A, so I am going to write that as pi over 2 minus A, and eventually you see that this is actually angle A, because you see this pi over 2 and the other pi over 2 within the parenthesis, they will cancel out each other because of the negative sign, and the end result is actually the angle A. So this angle, the angle BDF, that is actually equal to A, and let me denote that right here. So I am going to use a red color here to denote that this is actually angle A right here. Now we are going to look at the triangle BFD. If we use the sine law on the triangle BFD, let's see what we find out. So we can say that FD over sine of B, I am now using sine law on this small triangle BFD. So you can say FD is one of the sides of this triangle over sine of the opposite angle, which is the angle B of the original triangle. So we can say FD over sine of B will be equal to BF over sine of A, because you see the angle BDF has been determined to be equal to A. So BF over sine of the opposite angle, which has been determined as angle A. So we can say that FD over sine B is equal to BF over sine A. Now we are interested in FD, so we are going to say FD is equal to BF. Now what is BF? Well, BF is actually A times cosine of B, and then also we have sine of B coming over to this side, so you can write it as sine of B over here, and then whole divided by we have sine of A. And if you think about it, can we write it as A over sine of A times sine of B times cosine of B? And now what is A over sine of A? If you think about our original triangle, A over sine of A will be equal to 2 times the circumradius from the sine law on the original triangle. So we can say that this is equal to 2 times uppercase R, which is the circumradius of our original triangle, times sine of B times cosine of B, and that turns out to be R times sine of 2B. So can we write it as R times 2 times sine of B cosine of B, that can be written as R times sine of 2 times B. So we have found one side of the pedal triangle, that is equal to R times sine of 2 times B. Also in here, if you look at this particular value right here, which is 2 times R times sine of B times cosine of B, if we replace 2 times R with B over sine of B using the sine law on the original triangle, we can say that 2 times R is also equal to B over sine of B. So if we do it like that, then here again you can see that we are going to get from here, right here I am writing on the right hand side here. So this also can be written as B over sine of B times sine of B times cosine of B, and again you see this sine of B and that sine of B, they are going to cancel out each other, other. So we are going to be left with b times cosine of b. So from here we are going to get that this is also equal to b times cosine of b. So we are seeing like two values for fd. So let me make a note of that right here. So fd is actually equal to r times sine of 2b, or it is b times cosine of b. Let me underline here. So r times sine of 2b or b times cosine of b. Those are the two possible values of fd. And in each of the values you see the angle that is involved there is actually the b angle, which is actually the angle opposite to the side fd in that small triangle BDF. So then let's summarize this. So we can say that fd is equal to r times sine of 2b, which is also equal to b times cosine of b. And using the exact similar approach, if you use the triangle CDE, from there you should be able to find out the length of DE, which will be equal to like this. Let me just write down here. I am not going to go into the derivation, but use the exact same technique for the triangle CDE, and from there you will be able to calculate the length of DE, which will be like this. And DE will be equal to r times sine of 2c, which is also equal to c times cosine of c. And similarly, what would be the length of FE? Well, it's easy. You can predict now already. So FE will be equal to r times sine of 2a, also that is equal to a times cosine of a. So far we have been able to calculate the size of each of the interior angles of the pedal triangle, and also we have been able to calculate the length of each side of the pedal triangle. And now we are going to calculate the circumradius of the pedal triangle. Let's see how that looks like. Circumradius of the pedal triangle. Now if you look at the pedal triangle, which is the triangle DEF, we already know size of each of the interior angles now, and also we know the length of each side. So we should be able to use the sine law on this pedal triangle. So if we use the sine law on the pedal triangle, how is it going to look like? We can say FD over sine of angle FED, and angle FED is actually pi minus 2b. That will be equal to DE over sine of angle DFE, and angle DFE is actually equal to pi minus 2c. So that would be sine of pi minus 2c, and also it will be equal to EF over sine of the angle opposite to EF, and that angle is actually FDE, and FDE angle is actually pi minus 2a. So that would be pi minus 2a right here, and each of these ratios will be equal to 2 times the circumradius of the pedal triangle. So I am going to denote that with an uppercase R with a subscript P to denote that this is actually circumradius of the pedal triangle. So 2 times R sub P. Now from here we are interested about the size of R sub P. So from here we can take one of these ratios. Doesn't really matter which one we take. We can maybe take the EF over sine of pi minus 2a. We can take that ratio. So let's do a little calculation here. So we are going to take this portion, and from there we are going to find out the value of R sub P. So from here we can see that R sub P will be half of EF over sine of pi minus 2a. Now what is EF? Well, we already know the length of EF, which is on the left hand side here. We can say EF is equal to R times sine of 2a. This R is actually the circumradius of the original triangle ABC. So in place of EF I am writing R times sine of 2a, and over sine of pi minus 2a, that will be sine of 2a, and here you see that this sine of 2a and the sine of 2a are going to cancel out each other. So we are going to be left with half of R. So that means this is equal to half of R, or R over 2. So the size of the circumradius of the pedal triangle is actually half of the circumradius of the original triangle. So far we have been able to calculate the interior angles of the pedal triangle, the side lengths of the pedal triangle, and the circumradius of the pedal triangle. Now one quick observation that I want to mention here about the pedal triangle and the original triangle. Let me scroll up a little bit, and there you see, looks like each of the altitudes of the original triangle is actually bisecting each of the interior angles of the pedal triangle. For example, let's look at the angle DFE. You see the angle DFH and angle FHE, they are actually equal. That means CF or HF is actually bisecting the angle DFE. And similarly, if you look at the angle FDE, there again you will see that angle FDH and angle HDE, they are actually equal. That means AD, which is the altitude of the original triangle, it is actually bisecting the interior angle of the pedal triangle, and that interior angle is FDE. That interior angle is being bisected by the altitude of the original triangle, and that altitude is AD. So AD is bisecting the angle FDE. And similarly, if you look at the angle FED, that is also being bisected by the altitude of the original triangle, which is BE. So that BE altitude of the original triangle is actually bisecting the interior angle FED. So this point of intersection of the altitudes of the original triangle, which is called the orthocenter for the original triangle, also seems like the incenter for the pedal triangle. So that is one very important note. You have to remember that the orthocenter of the original triangle is also same as the incenter of the pedal triangle, or in other words, you can say that the incenter of the pedal triangle is same as the orthocenter of the original triangle. And another observation that I should mention here, that if you look at the size of each of the interior angles of the pedal triangle, for example, the angle EFD, which is equal to pi minus 2c, or angle FED, which is equal to pi minus 2b, or angle FDE, which is equal to pi minus 2a. Now if you look at each of these angles here, you can clearly see that A or B or C have to be less than 90 degrees. That means the original triangle has to be an acute triangle. Otherwise what will happen? Pi minus 2c, in case the C angle of the original triangle is larger than 90 degree or equal to 90 degree, then what will happen? Your angle EFD will either become 0 or negative, and that's not a good thing. We won't be able to draw the pedal triangle if one of its interior angle is 0 or even negative, which doesn't make sense, right? So to be able to draw a pedal triangle, your original triangle has to be an acute angle triangle. I hope everything made sense. Thank you for watching. See you in the next video.